Welcome back, everybody. We're going to talk more about state space today. And one of the interesting things we're going to talk about is changing our state variables and what that means and what you can do by changing your state variables to your benefit. To get started, though, I will do a quick review of what we did last Thursday. This was sort of our introduction to state space. And one of the things we started off with was we compared what we've been doing so far in the quarter using classical techniques like locus, and how those compare to what's known as a modern control technique, which is our state space technique. And we rattled off a number of things that were a comparison. There's some limitations with the classical technique, ways to overcome them in some sense, partially. We like classical techniques because they're simple and they're intuitive. However, they're really for LTI systems, so linear systems, time invariant systems, therefore SISO systems, single input, single output systems. And it's hard to do anything with a high order, so they're sort of limited with two lower order systems. Our state space techniques, we're going to find, however, they're good for nonlinear systems, they're good for time varying systems, they're good for multi-input, multi-output systems, and they scale very, very nicely. So you can do very high order systems using a modern control technique, really because you're using a matrix vector formulation, and so all the complexity really is buried in the order of the vectors and the matrices that you're using. So you can have a very compact representation of a system in state space, even if the order is enormous. No matter what, it'll look like a first order differential equation. So in our use of classical techniques up until now, and really the one that we've been using with any level of effort has been root locus. We've linearized, we've assumed that we have a time invariant system. We've done only block diagrams of the single input and single output, and we tend to approximate things to a lower order, and often talk about the modes as combinations of first and second order systems. You can do piecewise linearizations. You can do sort of time chunks of time in order to string together different assumptions about being time invariant in one period of time and then change it for another period of time, sort of like the piecewise linearization for embedded time. But sometimes that becomes difficult to do, so you would hop to a modern control technique. Same thing, you can do more interesting things than just single input, single output using classical techniques if you use approaches like successive loop closure, but you're not required to do that in modern control. You can explicitly represent multiple forcing inputs and multiple read outputs using a modern control technique. And another thing that we'll find is when we did classical techniques, we often, when it was a higher order, we often did a design problem that really just focused on what we would call the dominant roots. And we'll find in modern control, at least the technique we're going to use, we'll be able to focus on locating every single pole of the system. And so we have a greater ability to directly specify the full characteristic of the closed loop behavior because of that. So, given all that, we wind up with our state space equations, and they're of the form x the vector dot equals ax plus bu, and y equals cx the vector plus du. And we've been using that set of equations for quite some time now. That's been one of our four main representations of the dynamic of a dynamic system. And we've been able to convert between our four representations and talk about the pros and cons. We now have two equations, and so we're carrying along a little bit more complexity, but it gives us a lot more information about what's going on within the system compared to something like a transfer function. Transfer function, we have one equation, but it's strictly an input-output relationship, and it doesn't capture what's going on inside the box, so to speak, like our state space equations do. But to get that, we're now carrying two equations as opposed to just one. So there are state space equations. And when we look at the mathematics, we realize that A, B, C, and D are matrices or vectors or a combination thereof. What they are depends upon the the dimensions of our variables, which are x, u, and y. And so x is going to be a column vector that is the order of the system by 1. So if it's say a third order system, it'll be a 3 by 1 column vector. And x vector dot is also 3 by 1. We've been used to having u and y be scalars, but that was in the SISO world, the single input, single output world. So if it was a single input, u would be a scalar. Single output, y would be a scalar. But these can now become column vectors as well, depending upon how many inputs or outputs there are. And then based on the order of the system and the number of inputs and outputs, B, C, and D have to take on the dimensions that make sense in terms of computing the equations. The other thing we also talked about was the mathematics that are going to be used when we really use the state space technique. So the math, in terms of we're going to be adding, subtracting, multiplying, and dividing these quantities. And so remember that when you have matrices or vectors, you can add and subtract. When you multiply, though, matrix multiplication is not commutative, so the order matters. A times B, if A and B are matrices, in general is not the same as B times A. So don't get caught by that. And when we divide, realize that we don't divide by matrices. What we can do is we can multiply by the inverse. And so if we were to try to get rid of a matrix on one side of an equation because we're trying to isolate a variable, rather than dividing by that matrix, we might pre-multiply by the inverse of that matrix. And so when the inverse times the matrix are next to each other, those will get converted to an identity matrix. And that's sort of our matrix form of division, if you will. But we don't explicitly divide by matrices. We're also going to be taking determinants of matrices. We're going to have to do things like find the inverse, maybe you have to find the transpose, and certainly we're going to be worried about eigenvalues and eigenvectors of matrices. So we did an example or two of that last time, and we'll keep doing examples, but if you're rusty on these things, you need to go and brush up on them. The fundamental math for manipulating matrices and vectors is critical when it comes to using modern control techniques to design controllers. Okay, then the last two things we did last Thursday was we sort of said, hey, we have this set of equations. These are really time domain equations. It's a first order time domain equation of how the state evolves, and here is what you get to see on the output. But when we have a time domain equation, especially one with the highest order derivative that's been isolated, one of the first things we've been thinking about historically is, well, I could convert those to the equivalent expanded block diagram as well as to a transfer function. And we can certainly do that, but it might be interesting to take a look at that if we kept our matrix vector form, A, B, C, and D. So very briefly, if we now have the highest order derivative isolated, so if we say, well, I'm going to integrate that, so here is x the vector dot going into an integrator, and here's x the vector coming out. I've got u coming in overall. I'm going to multiply by a b and add that term, and I know overall my system is going to have a u going in and a y coming out. So u is the input and y is the output. X is the state vector and all the state variables that are evolving inside the system. So far I have x the vector dot equals b times u, which we see right here, and we can feed back an A the matrix times x to that summation node, and here is my first equation. The state vector derivative, x the vector dot, equals two terms, which we see up here in the equation, and now we see it in the diagram. X the vector dot equals a times x plus b times u. And we see that reflected up here. X the vector dot equals ax plus bu. And then our second equation is y equals the sum of two terms. Here's our y. It's the sum of two terms, so I'll put two some terms coming in here. And the first one is c times x, so I'm going to have c times x come into that summation node. And the second one is d times u. So here's my input u. I've got a feed forward term d coming down like that. And so that is what our expanded block diagram looks like in matrix form, given the state space equations, x the vector dot and y. And we see the roles that each of these terms, A, B, C, and D, play. A is our feedback term, and we've often talked about how the feedback dictates the dynamic. So all the dynamic information about the evolution of the system is somehow captured in the matrix A. B, on the other hand, in some sense sort of pre-filters the input in terms of how the state can be influenced. And C dictates of all the state information what you're allowed to see on the output. And then D is just our feed-forward term, allowing us to also see the input being conveyed all the way through the system. But it's very interesting to note that A is the feedback term. The A matrix holds our dynamic information. Okay, the other thing that we talk about doing, we now have our equation of motion, we have our expanded block diagram, is we could go to a transfer function form. And I'm going to do that, but again I'm going to keep the A, B, C, and D as opposed to breaking it down, which is what we were doing before. So if I start with the first state space equation, x vector dot equals ax plus bu, and I take the Laplace, I'm going to get something that looks like this. And now I want to combine the x terms, so I'm going to bring the a over. And I'm going to take out the x from the s and the a, but s is a scalar in this case, a is a matrix, so to do math with them I have to multiply s by the identity matrix. So I'm going to get si minus a times x, the Laplace variable, equals bu. That's the Laplace variable. And now what I'm going to do is I'm going to isolate x. But to do that, I would really like to divide both sides by this. But this is going to wind up being a matrix. Si is a matrix minus the A matrix. That'll be some net matrix. And I can't divide by a matrix. But what I can do is I can pre-multiply by Si minus A inverse. So when I have that term times this term, I'll get the identity matrix and it'll effectively go away. So I'm going to pre-multiply both sides by the quantity Si minus A inverse, which will leave me with x of s on the left-hand side, but I'll also get Si minus A inverse times b u of s on the right-hand side. So that's the result of my first state space equation, taking the Laplace and simplifying for x. And now what I'm going to do is I'm going to plug that into my second equation. I have y equals cx plus du. I'm going to take the Laplace of that, so I'll have y of s equals c x the vector s plus d u of s. For now I'm going to assume that u and y are scalars, because I'm converting this to a transfer function, and that would only make sense if it's a single input, single output system. But I'm going to take this x equation, this x solution that I found here from the first equation, and I'm going to plug it in right there. And when I do that, I wind up with c times si minus a inverse times b. And in fact I'm going to pull out a u, so I'm going to get that plus d u of s. And now I can divide both sides by u, y of s, u of s. That's our transfer function right there. And we see the transfer function is c si minus a inverse times b plus d. So there are two interesting things about that. First of all, that in and of itself is how to convert from state space to transfer function form. It's a different way of doing it than we did it before. What we did before was we sort of multiplied out all the equations, and we had a form of state space where all the information of the A matrix is packed into one equation. And so it made it very easy to get